At the end of the last video, I left you with this homework problem, number 45, and so I'm going to work through that with you. Now, if what I do doesn't match what you did, that doesn't mean you did it wrong. I mean, if you didn't finish and you know you didn't prove it, then you know what you did was at least incomplete. But there are many ways of proving things. Proofs are like the essay questions in math. And if you're asked in an English class to write an essay, it's not like there's one right answer. There are lots and lots of ways of doing things. So I'm going to work through this. Hopefully you'll understand and follow what I did. It may or may not match the approach that you took. If you took a different approach and you feel confident that it's right, fantastic. If you took a different approach and you're not entirely sure whether your version is okay, just ask. Shoot me an email, come to office hours and share your screen, show me what you wrote. I'm happy to give you feedback on that because there really is no one correct way of doing this. So I'm going to say, here's my left-hand side, and there's my right-hand side. Now, it does look to me like the left-hand side is more complicated, so I'm going to start with that one. I notice that that's a difference of two fractions, and here I just have one term. It's a bunch of stuff multiplied together, but there are no separate terms being added and subtracted. So it looks like I want to actually do that subtraction and combine this into just one piece. Okay, and I kind of like that because I notice that these denominators that I have happen to involve the same two terms, a 1 and a secant, but connected with the opposite sign. So I kind of like that because my least common denominator is going to be just the product of those two, and that's going to give me a difference of 2 squares. Because anytime I multiply a sum times a difference of the same two things, I get a difference of 2 squares. So let's see what happens. The left-hand side, I've got to just copy it down because remember, I'm not allowed to use this version as part of my proof because this version is connected to the right-hand side and I haven't proved that they're equal yet. Okay. All right, so I'm just working with that left-hand side. And as I said, the common denominator would just be the product of these two. So we'll take 1 over 1 plus secant x. I'm going to multiply that by 1 in the form of 1 minus secant x over 1 minus secant x. This denominator over itself. And then I'm subtracting 1 over 1 minus secant x. I'm going to multiply that one by 1 in the form of this denominator over itself. So 1 plus secant x over 1 plus secant x. Okay, so then that's going to equal, let's see, here on top we'll get 1 minus secant x over. First terms give me a 1. Outsides and insides cancel. Last terms give me a minus secant squared x. And then we're subtracting 1 plus secant x over that same denominator, 1 minus secant squared x. So with a common denominator, I can now write this as a single fraction with that common denominator on the bottom. Just need to be very careful. If I'm subtracting this one, I'm going to have to distribute that negative to both of these terms on top because I'm subtracting the entire top. So it's 1 minus secant x, that was this top, minus the 1 minus the secant x. Do make sure you subtract both parts of the top. Now that's kind of nice because the 1 and the minus 1 will cancel, and then I've got on top negative 2 copies of secant x over 1 minus secant squared x. All right, now in the denominator here, I see the number 1 and a trig function squared. When I see the number 1 and a trig function squared, that makes me think Pythagorean identity. Because all the Pythagorean identities involve some combination of 2 trig functions squared and the number 1. Okay. Now, I do at this point have all the Pythagorean identities accidentally memorized, but I'm going to pretend that I don't. And I'm going to just do a little bit of side work. Okay. So I'm going to erase everything except I've gotten to this point. Okay, so far we've said that the left-hand side is equal to that, with a lot more work to get that. Okay, a little bit of side work. If I don't remember all the different versions, I should always know this one. Sine squared x plus cosine squared x is equal to 1. And I know there is a Pythagorean identity that has secants in it. Now secant has cosine in the denominator. So I'm going to get to that by dividing through by cosine squared. And of course that division distributes to every term on both sides. Then sine squared over cosine squared is tan squared. Cosine squared over cosine squared is 1. And 1 over cosine squared is secant squared. So now I look over here, I've got 1 minus secant squared. So to get to that, looks like I'm going to want to subtract the secant squared over to the left side, and I'll move the tangent squared over to the right side. So we'll get 1 minus secant squared x is negative tan squared x. And totally fine to just have some side work if you're working with one of your fundamental identities, but sort of rearranging it a little bit. Because this is sort of the standard version, and this is, we've rearranged it. So now I can say, oh, okay, cool. So that's going to equal, I'm just going to continue this on over here, so this is still the left-hand side, negative 2 secant x over negative tan squared x. Nice. Those negatives are going to cancel, so that's just 2 secant x over tan squared x. I'm going to take a look at where I'm trying to go. This one involves secants and tangents. This one involves cotangents and cosecants. I'm going to switch to sines and cosines. So I'm going to rewrite this one in terms of sines and cosines, and then I'm going to stop. And I'm going to go to the 3-paragraph method. I'm going to go to my right-hand side, write that in terms of sines and cosines, and hope that they look the same. So this would be 2 copies of secant is 1 over cosine of x, and tangent squared, that would be sine squared x over cosine squared x. I think I'm going to actually just write that as 2 over cosine x, so it's just a single fraction over a fraction. Okay. And then, let's see, I'm going to erase this side work. Oh, I wish I had a big enough board to do an entire problem on one board. Okay, so all of this coming over here, that's equal to 2 over cosine x times, the way I divide by a fraction is to multiply by the reciprocal. So that would be times cosine squared x over sine squared x. I can cancel one factor of cosine, and so I get 2 cosine x over sine squared x. That's how I've been able to simplify that left-hand side. Okay. All right. Excellent. So for the right-hand side, so new paragraph, this is not connected to the work before it with an equal sign. Okay. But everything else, I was writing in that equal sign. We're doing formal proofs here. That's going to include the punctuation, which is those equal signs. So if in your proof you're saying that things are equal, I want to see the equal sign. I don't want just a list of things that were simplified. I want this equals this equals this. And then when you switch to something new, there's a distinct lack of an equal sign. I'm not yet claiming that that's equal to the right-hand side. But the right-hand side is 2 copies of cotangent x times cosecant of x. So I'm going to write that in terms of sines and cosines. So again, I'm connecting it with an equal sign. That's 2 copies of cosine of x over sine x is how I would write cotangent of x. Cosecant of x is 1 over sine x. If I want, I can write that 2 over 1. Then if I multiply this out, I'm going to get 2 cosine x over sine squared x. That's what I got when I simplified the left-hand side too. But I'm not going to stop here and leave it to my reader to notice that they're the same. 3rd paragraph, I'm going to point out, hey, look, they are the same. The left-hand side equals the right-hand side because I was able to simplify them to the same thing. All right.